start. So good afternoon, everyone. Welcome to this edition of the NITheCS Colloquium. My name is Francesco Petruccione, and I'm at the moment the interim director of NITheCS. And today it is a really big pleasure to introduce to you Professor Aleks Kissinger from the University of Oxford, who will give us what promises to be an excellent talk on picturing quantum software. Yeah, and Aleks, as I mentioned, is based in the computer science department of the University of Oxford, where he leads quite a large group in quantum software and the foundation of physics. Some of you might know his name because he co-authored a very famous book that is called Picturing Quantum Processes. Yeah, a book that has also the nickname the Dodo Book. I don't know exactly why there is a dodo on the title page, but maybe Aleks will tell us. Yeah, at some stage. And today he will share with us some, introduce us to this strategy of picturing quantum processes. But in particular, he will address aspects of, I think, quantum circuit optimization and other aspects that are relevant to whoever is interested in quantum computing. Yeah? And as usual, on the panelists, you see Ilya, who is the standard co-host of these events, and he will moderate the question after the talk. Yeah. So Aleks, people are here to listen to you, not to me. You already started sharing your slides, so everything is okay. If you want to start the talk, you're most and welcome. Thank you very much for your time.
Okay, thanks Francesco for inviting me here. We were chatting a little before, and Francesco was saying that NITheCS is a pretty new sort of multidisciplinary institute with maybe some idea that somewhere in the story the glue will be category theory, or sort of, you know, some way that the people can communicate with each other. Is categorical in some sense. So what I'm going to talk about is not specifically about category theory, but really about pictures. And these pictures sort of came out of categorical quantum mechanics, this approach to doing quantum theory, and that's influenced a lot of what's in the background of this. So you notice my title is Picturing Quantum Software. This is a bit vibing off the title of here's the book, Picturing Quantum Processes. And yeah, as Francesco said, it's called the Dodo Book because there's the dodo, and he features a lot in many of the examples. This is the name of a sequel book that's in the works called Picturing Quantum Software, and it's focusing more specifically on solving practical challenges around quantum computing. Okay, so maybe I'll say what I mean by quantum software before talking about how and why you should want to picture it. So when someone says quantum software, they typically mean one of two different things. On the one hand, this could mean the code that runs on a quantum computer. Okay, so i.e. quantum algorithms. So you probably know about the famous factoring algorithms, search algorithms, and now there's a whole zoo of these things. From everything from simulating physical systems to solving hard optimization problems, quantum machine learning, NLP, the whole bag. So I think that's what the majority of people are talking about when they're talking about quantum software. But another thing that I think is very important to think about is not just the code, but also the code that makes the code. Okay, so what do I mean by that? Well, I mean compilers, for instance, so something that will take your high-level description of the algorithm and turn it into something that runs, but also things that take code and make code better somehow. So compilers, optimizing compilers, verification. I'll talk some things about classical simulation. These are all kind of solving problems around quantum computation that are really important, and in fact a lot of this happens on a classical computer even before you fire up the $1 million quantum device you have in your lab. Okay, so a problem that would often get levied at someone who is looking at code that runs on quantum computers, and this is now an out-of-date criticism, right? This idea that, oh, well, there's no quantum computers, why bother? Of course, we know this isn't the case anymore. Kind of every other day, you see both in academia and in industry groups popping up to say we have a new superconducting or ion trap or photonic quantum device. So these things are very much real today. The problem is that they're kind of crappy, right? So they're very limited in many ways. So this kind of buzzword around this idea of a kind of crappy quantum computer is NISQ, which stands for noisy intermediate scale quantum computers. And these kinds of devices have very short coherence times before everything just turns into noise, low amounts of quantum memory, very noisy operations, limited operations fit together in only very limited patterns based on really physical constraints of the device, and so on. So there's a lot of very tight constraints we have to work around when trying to code for these devices. But this is actually, I think, quite a nice opportunity to be working in this area of quantum software, because even if you can make small advances in making something a little bit more efficient or fit in a little bit more space, this can actually have a big impact on whether this thing can actually be runnable on one of these NISQ devices. Okay, so the kind of, when I talk about the code that runs on a quantum computer, for the most part, I'll be talking about quantum circuits. So this is you can think of this as kind of an abstract assembly language of quantum computation. So this is a sequence of instructions which really describe what's happening on your quantum device. Okay, so these instructions are often called quantum gates. So you could say, well, I initialize maybe some memory in a fixed state, and then I start applying these gates to the memory. And this could correspond, in fact, to some physical hardware operation. So for instance, a microwave pulse being applied to some part of a superconducting qubit for some number of nanoseconds or something. But then, you fix some collection of these things get called gates, and you say, well, run these gates, and that's going to be my computation. Okay, and of course, something that we want to do once we have this notion of code that runs on our machine is to think about how we could optimize such a computation. So I'll first talk about the kind of the naive way you go about optimizing computations, or you could say this is the old-fashioned way, but maybe terms like old-fashioned aren't really. This hasn't been around long enough to really talk about old-fashioned or new wave kind of thing. But here's how you could at least naively start to think about optimizing things. So you could look at this circuit, and you could notice that certain combinations of gates actually are equivalent to certain other combinations. Okay, so one thing, if you knew a little bit about how these gates interact with each other, you would know that if I do two of these H gates and then I do a C naught after it, well, I can also trade places. And I can do the H gates later, and here I'm doing a C naught kind of in the other orientation. Okay, so you see I've kind of pushed the H's through and flipped the C naught around. And then if I do two of these C naught gates, well, they would cancel out, and then the overall effect is I've done the same computation more compactly. Right? So you can start to come up with a lot of these kinds of rules, these kinds of peephole optimizations, which change some collection of gates to some other collection of gates. So here's a few of them, and then here's a few more, and then here's a few more, and then you can come up with some more, and then oops, oh no, I always do this. So you can come up with some more and some more, and you kind of wonder, when does it end? Do I just need to always be coming up with these things and applying them in a somewhat ad hoc fashion to do optimization? And the answer is no. You can actually do something more clever if you sort of cut open these gates and you look at what's inside. So I really want to say, don't treat these gates as this kind of black box, which I'm just going to start enumerating more and more rules about. I want to really see what is the underlying algebraic structure, and really originally, if you look back kind of a decade, what are the underlying categorical structures that make these things work? And we found something that is quite successful at this. We replaced these gates with this sort of lower level algebraic entity called a spider. Okay, so these dots, these red and green, or if you're colorblind, these light gray and dark gray dots are called spiders, and together they make what's called a ZX diagram. So this is a graph representation of that same computation. Okay, so they're made of these things called spiders. Well, so all of these things are represented mathematically as matrices, and here's the matrix of a green spider. And here's a kind of way to change the colors of spiders, and then a red spider is just the color being changed. It's not too important. What the important thing is that if I have one of these diagrams, it's really now a graph. Okay, so the circuit before was this rigid thing where the gates were really being applied to particular memory locations, and the rules were quite specific to certain configurations. This thing, the ZX diagram, is a graph. So in fact, if I deform it, it describes the same computation. And not only that, these new generators, these spiders, satisfy some very simple algebraic laws that allow me to turn these graphs into other graphs. Okay, so if you look at each of these, you can kind of start to get a feel for what's going on with these rules, right? So if I have two dots of the same color, they sort of merge together, and I add together the symbols on the dots and so on. And here I've drawn 8 rules involving these ZX diagrams. And in fact, these 8 rules involve will imply all of the hundreds and hundreds of gate rules that I showed you before. Okay, so by breaking open the gates and just looking at this more fundamental structure, you can actually get a lot of power from this. Okay, so let's go back to this example of this little piece of circuit where I cut open the gates, and now I can start to apply those 8 rules to this ZX diagram to get a simpler one. So let's see, I'll have to remember exactly what I do here. So here I'm just fusing together some dots of the same color, right? So all these green dots in a line here are kind of fused together to make a single green dot. And then I guess probably something will copy, yeah. So a red dot hits a green dot and it copies, and then I fuse some more. And then I start working on this thing using these very simple rules. And what happens is this thing, well, in this case, it simplifies completely, right? Which you could have proven if you'd managed to enumerate enough circuit laws to get there. But here it's become very clear what's happened once I'm looking at it at the level of this diagram. Okay, so now a natural question is how to take these kinds of algebraic techniques for working with circuits and scale them up. Okay, so here, this example that I gave, it had about 30 spiders in the diagram. And now to work with the kinds of circuits, even to work on this quite low level, this small hardware that we have today, we're probably talking about thousands to tens of thousands, maybe even millions of spiders. Okay, so of course we'll need some kind of automated techniques for doing this kind of algebraic manipulation. Okay, so we have a series of tools for doing this kind of thing, and probably the first one of this kind is a tool called Quantumatic. And this thing, well, you can see, so this was the paper about it. It was really intended to be a proof assistant for working with these kinds of diagram rules. So what you would do is you would really set things up from scratch. You would put in your rules, and then you would give some kind of simplification strategy. And if you've ever worked with, for instance, an interactive theorem prover and tried to write tactics in something like Coq or Isabelle, you might this kinds of stuff might look familiar to you. So you write some kind of simplification strategy in the strategy language, and then you apply it to graphs, and you can use it to do some simplification. So this is, you can still get this tool, and it's quite fun to play with. But I would say it's a general purpose small scale tool, and we've used it mostly for teaching and experimenting with things like ZX. And the reason I say small scale is that because it's general purpose, the kinds of ways that we do this rewriting don't scale beyond, let's say, maybe a few hundred spiders before you start having to wait quite a long time for this kind of thing to work. A step up, and maybe something that's more specific, but has also been more successful, is a tool called PyZX. So this is like PyZX or physics without the H in it. And this is basically a Python library, which is a medium scale circuit optimization tool. So this thing is quite easy to work with, and it's very hackable and also quite fun. So we use this for teaching as well. And it's more specifically aimed toward ZX calculus. So before it was kind of, I really specify my rules from scratch. This thing is really something for ZX calculus, for doing things with quantum circuits and solving specific problems around quantum circuits using ZX diagrams. So a kind of next scale up from there is a port of PyZX to Rust. So Rust is a sort of systems programming language that can make things run very, very fast and with very little memory. And I would say this is our, as far as open source tools go, this is kind of our main large scale circuit optimization and classical simulation tool for ZX calculus. So I'll talk a little bit about also how we're using these techniques for classical simulation later. Okay, so all of these things are open source tools, and you can find them all under this Quantumatic organization on GitHub. Okay, and basically the idea behind all of them is kind of the same. The main thing is to take equations. So an equation you really think of as a symmetric object that can be applied in either direction. So you take an equation and you turn it into a rewrite rule. So now this is really saying that I think this thing on the right is simpler than this thing on the left. So I really want to apply this rule going from left to right. And then after doing this, so turning things into rewrite rules, you also focus on tractable fragments of the language. So you think about designing sets of rules for fragments of the language where it's going to give you a lot of traction. Okay, so the two examples of tractable fragments that have been most useful to study here so far are, well, a very simple one is Xenon circuits. So these are built from a single kind of gate, which is called a control not gate, which is a ZX diagram, looks like this, just a green dot connected to a red dot. And these things, they're known to be efficient to classically simulate. They in fact correspond just to linear maps over this two-element field, F2 or Z2. They're always equal to a circuit of polynomial size. So this is usually not the case for a generic quantum circuit. It has to be exponentially large. And they're expressible using just phase-free ZX diagrams. Okay, so these are diagrams of the red and the green dots where I haven't put any labels on these things. So in general, these things are labeled by angles, and if I omit the angle, that's like an angle of 0. And these things called phase angles are what labels the diagram. Phase-free ones don't have that angle. Okay, so that's Xenon circuits. Another thing which is kind of one step of complexity higher than that, but still quite simple, are Clifford circuits. So these are built from the CNOT gate, this thing which is called a Hadamard gate, and this thing which is called a phase gate. These are also efficient to classically simulate thanks to this famous Scottis-Manil theorem. Again, always equal to a quadratically large circuit at most. And these are also expressible in a certain fragment of ZX diagrams. But now, rather than saying that all of our angles are 0, rather than saying all of our angles are 0, they're all integer multiples of pi by 2. Okay, so we fix our angles to be just this quite small discrete set of angles. I guess there's 4 possibilities. Okay, and in this Clifford ZX calculus, we get that this fairly simple set of rules here is actually complete for Clifford ZX diagrams, which means that if any 2 diagrams actually describe the same computation, then a human mathematician can prove that those 2 things are equal to each other just by applying these rules, kind of over and over, maybe in maybe sometimes left to right, sometimes right to left. And that's what here I mean by completeness. But now you can take this complete set of rules and try to turn it into something that can be automated so that a machine can use it. So let's look at this thing and start to try to direct some of our rewrite rules. Okay, so here's that set. And now it's kind of clear what to do with these fusion rules. Right, so if I have 2 dots here and I have 1 dot here, well, that just seems to be a simpler diagram. So I'm going to direct things in that direction. And here I have 1 dot, and this turns into 0 dots. This is meant to be like the identity map, just a plain piece of wire here. Nothing happened to my qubit. Okay, so these all work very well, turning these into rewrite rules. But a question which puzzled us for quite a while was actually what to do with this rule down here in the middle. Okay, so you might think, if I'm going to use this sort of rule of thumb that less dots is better, that I should direct this thing from right to left. But this actually goes very wrong. And I can sort of go into that. I wrote my master's thesis about why this goes wrong, to direct things from right to left. Basically, it kind of destroys a lot of nice properties about how this algebra behaves. But something that works much better is if I extend this rule a little bit and I just put some extra spiders around the outside of it. So here I'm applying the same rule, but in a bigger context. Well, now that these 2 things are the same color, I can merge them together. And now I can see that actually, if I apply this thing from left to right, I've deleted 2 of these dots. Okay, I might have created a bunch of new edges, but I've deleted some dots, so I can really think of that as a simplification. Okay, and that works a lot better. The reason or let's maybe not say the reason, but what this does when I say it, what I mean by this works a lot better, is if I take some CNOT circuit like this, and I just start stupidly applying those rules until they don't apply anymore, then I'll get something that looks like this. Okay, and before I said that a CNOT circuit actually corresponds to a linear map over the 2-element field. Okay, and what does that mean? Well, that really just means that it takes some bits as its inputs, and it produces some XORs of those bits as its outputs. Okay, that totally characterizes such a Z2 linear map. And in fact, if I apply these rules until I get to this kind of form, I can just read the map off of it. Okay, so here, if I read these red dots as XORs and these green dots as make a copy of that input, then you can see that here I've got a X0, it's getting copied, say, to 3 places where that X0 appears. And here, when I have an output, which is connected to an X0, an X2, and an X3, I can see exactly those wires coming in to make that XOR. Right, so that's already quite a pleasant feature of this algebraic structure. It kind of knows that these things really should be just considered as these kinds of collections of XORs whenever I have a CNOT circuit. Okay, and you can push this a little farther by figuring out what to do basically with these other rules to get the whole Clifford fragment working out well. And what the trick is here, I mean, it's not really important, but for what I'm going to talk about, but maybe you're interested. One way you can get those other rules to work nicely with what we have so far is I can use this idea that if I wrap all of my red dots in these Hadamard gates, I can make them into green dots. And then I just make a kind of a notational shift. So now you see that before I had two kinds of dots and only one kind of edge. Well, I can think of this edge with a Hadamard gate on it just as another kind of edge. And now I have only one kind of dot and two kinds of edges. Okay, so this thing is actually, it's quite a lot like what's called a graph state, if you've ever encountered these things before. And making this kind of notational shift, I can introduce a new rule that gets rid of all of my red dots and makes them green dots like this. And then I can kind of update my other rules to account for the fact that we want to work with these only green dot type things. And if I massage these things a little bit, I get a kind of a class of rules that works very well for Clifford circuits. And these things, if you're curious, these things have names pivoting and local complementation. These are graph theoretic moves that kind of existed before. And you notice, like we had before, I can really think of these things as simplification. So here I'm deleting a pair of nodes and just getting some edges. And here I'm deleting a node and just getting some more edges and so on. And I'm just kind of updating these little bits of these edges and these little bits of data on my nodes as I go. Okay, so now I can take this collection of rules and say I have some big quantum circuit. Okay, so here's a kind of a big quantum circuit. It's probably got, I don't know, 100 or so gates in it. And I just apply these rules until I can't apply them anymore. And what this thing will do is it will completely consume the kind of part of the structure that these rules understand. And in this case, it's consuming the part of the structure that's Clifford-like, so that has these pi/2 angles in it. And what's left is kind of, well, what's left is what's left. So the kind of genuinely quantum, or the kind of harder to understand part of the circuit. Okay, we call this the skeleton. Okay, and this idea that I can take a kind of a complex circuit and I can consume all the parts of it I understand, is useful for a number of different applications in a number of different contexts. Okay, so, well, maybe I should say that the first thing you might want to do with this is optimize circuits. So maybe I've got now this big circuit, and I have computed this very compact graph. So this graph actually represents the same computation as this big circuit. And you might think, well, maybe I can just turn that graph into now a smaller circuit. Okay, and then I've kind of won, right? Because I've optimized my circuit. So a question is, if I have a graph like this, how can I get a circuit back out of it? Well, in this case, well, so for one thing, ZX diagrams can represent any map, but circuits are always unitary linear maps. So it's not the case that I can always do this, because not all ZX diagrams are equal to circuits. So you can pose this as, I think, quite an interesting problem, which is, given such a diagram that represents a unitary, try to find me an equivalent circuit. Okay, and particularly try to do this in some efficient way. So I would conjecture that this is not possible in general, in the sense that if I can extract a circuit in polytime all the time, so if this is always possible, then something bad happens. So what do I mean by something bad happens? It's this kind of complexity theoretic statement, right? So that this should imply something that's kind of, let's say, silly from the point of view of complexity theory. And here, I think it means something like BQP and post-BQP, these complexity classes collapse. And this would, in some sense, this would be very bad, because this is what we can do efficiently on a quantum computer. And this is this gigantic class which contains NP and a whole bunch of other stuff. So we don't expect them to collapse. So we need some kind of heuristics or extra data to try to get a circuit back out. Okay, so the way we figured out what we actually need, kind of historically how we figured this out, is we just started trying to get circuits back out of these little diagrams. Okay, and actually if you start applying the ZX calculus rules to such a diagram, this does get you some distance, right? So if I imagine that I start here on the right and I start pulling quantum gates back out of this thing using the rules that I know, well, I know that these blue edges were Hadamard gates to start with, and I can look at these things with angles and I can pull them out as these things are called phase gates, and then I can sort of pull out some more Hadamard gates and so on, and phase gates. But at some point I get stuck. So at some point I get something that's kind of too graph-like to continue. But then something quite interesting happens, which is I can look at the adjacency matrix of this graph. Actually, it's called a bi-adjacency matrix. So this matrix is capturing how these things are connected. And if I start doing C0 gates over here on the right, this starts doing row operations on this adjacency matrix. Okay, so this is actually an equation that you can prove in the ZX calculus. But what it amounts to is if you get stuck, you can start doing Gaussian elimination on this adjacency matrix with C0 gates until you can proceed some more. And then if you proceed, at some point, you get a circuit back out. Okay. So this gives you a kind of a heuristic, and you can try it. You can ask, okay, well, when does this work? Okay, so at some point, you were able to do enough eliminations that you got the thing to work, and you were able to proceed. This actually works exactly when your graph has this property called generalized flow. Okay, so I'm not going to explain to you what this kind of nasty looking formula means, but it's basically it's some graph theoretic property that you can check efficiently, and if you have it, then you can extract circuits from a graph. Okay, so an easy thing to show is the place where I started was graphs that had G flow. So the circuits that I put in have this nice property. And in fact, what you can also prove is that the ways that I reduced my circuits preserved this property, which means that if I use this strategy of computing the skeleton from a circuit, I always have a graph with this nice property that allows me to get a circuit back. Okay, so we can really use this to do circuit optimization. And the first kind of optimization that we tried using this kind of crunch and extract type technique was called T-count reduction. So you have these kinds of gates in a quantum circuit called T-gates, which in certain models of computation are more expensive than the other gates. You want to reduce them. Okay, so what do? We start with our circuit. We compute the skeleton of our circuit, which in the process can cause some of these gates to cancel out with each other. And then we re-extract it. And then ideally we get something with fewer T gates in it. Okay, so if you're not so fast at counting, I think this bottom one has about 6 fewer T gates than this top one. Okay, so we tried this and it actually worked pretty well in comparison to the state of the art at the time. So we did this back in 2019, and we compared it to these other, what were called ancilla-free T-count reduction procedures, which were around at the time. And on about 70% of them, we were actually matching the kind of best known. And on 17% of them, we were actually doing a bit better. So we were able to kind of push the boundaries of this problem a bit using this technique. The very next month, Zhang and Chen came up with another arguably simpler technique for getting the same numbers. But then sort of later that year, some other people at Oxford sort of beat the state of the art again with a new based method, And it kind of continues. So this is something that's sort of ongoing. I think so. When we put this first paper on the archive, I got a message from Earl Campbell, who wrote this 2018 paper saying, "Welcome to the T Wars." So this is something that's sort of ongoing as people trying to push these techniques as far as you can in almost a kind of competitive way. So a nice property of this style of optimization is that it's actually self-checking. So you can ask, how do we so when we put our circuit into an optimizer, how do we know that we didn't break our circuit? How do we know it's doing the same computation as it was doing before? Well, in general, this is hard. And how hard this is called QMA complete. This is kind of like the quantum version of NP complete, to judge whether two circuits have the same unitary or do the same computation, let's say. But a nice thing about PyZX, which is where we implemented this optimization strategy, is that it's self-checking. So if a circuit will reduce to a circuit C, if it will reduce to another circuit D, then in fact, if I do C and then I do the inverse of D, our simplifier will reduce that to the trivial circuit. Okay, so if these two things are the inverses of each other, then this should reduce to the identity. And this happens, and it takes cubically bounded time, and in practice, it's actually quite a lot better than that. So we can use this optimizer to verify the optimizer, for one thing. And actually in the process, we found bugs not only in our own software, but we found bugs in some of the competitors, right? So we were looking at some of these other optimized circuits, and we saw a number that looked sort of suspicious. And we ran it through this thing, and it said, yes, well, maybe this is indeed a problem with this circuit. And then we used some other techniques and found that there was actually indeed a bug in one of these published results, which has since been fixed. Okay, but here's a kind of provocative question that I like to ask, and this kind of depends on how near or far you think fault-tolerant quantum computing is away, which is, who cares about the T count? Okay, so T count, the reason that we talk about reducing the T count is that these things will probably be important in fault-tolerant models of quantum computing. So these kinds of ways of doing error-corrected quantum computing tend to have very expensive T gates, and that's why we like to reduce the T count. But if fault-tolerant computing is 5, 10, 15, 20 years away, then why are we so worried about the T count anyway? I've got another answer for this, but maybe there'll be a short digression here, which is that there's other problems about circuits which are really important right now, and one of them is circuit routing. So this is the idea that if I have 2 qubit gates on many existing architectures, I can't apply them just between any pairs of qubits, but I have to apply them between nearest neighbors. So these, if you look at these kinds of architectures, these kinds of graphs represent literally where these qubits are on a chip. And these edges represent some sort of coupling mechanism between those qubits. And I can't do a gate unless the qubits are next to each other. Okay, so a very important part of compilation is compiling it such that I'm only doing gates between nearest neighbors on a given target architecture. Okay, so we can do circuit routing using this kind of optimize and extract paradigm. And the way that we do this is realizing that since we use Gaussian elimination to extract our circuits, so basically we're doing, every time we want a row operation, that corresponds to doing a CNOT gate. If we constrain which row operations we're allowed to do, then we only introduce CNOT gates where they're allowed. Okay, so for instance, maybe I have this kind of 3 by 3 grid of an architecture. then there's a way that I can do the same Gaussian elimination, but only using these kind of nearest edges. And this will actually respect this grid architecture. Okay, so I'll get more C0 gates, but I will get them in locations which I can actually fire on my hardware. Okay, and this also turned out to work very well. We were looking really only at C0 circuits, so the problem is actually a bit trickier when you look at generic circuits. And we did constrained C0 extraction using Steiner trees. So Steiner trees are a sort of combinatoric object which we use to make a plan for where we were going to do row operations, and then we kind of percolated things out these trees and then back. And this worked very well. So again, at the time, this was about 5 times more efficient than the existing ways that you could do routing, which were implemented by these kind of mainstream industrial compilers, or at least by these compilers implemented by these startups. And there's been some follow-on work. So for instance, at CQC, where they make this ticket compiler, they've done some follow-on work for broader families of circuits, and there's been various other people using these techniques or similar ones to do circuit routing. Okay, so I think that's a pretty good success. But I really want to come back to this question. So because I like it, because there's another answer you can give if somebody says, who cares about T count? So of course the standard line is that T count is very important for long-term fault-tolerant quantum computing. But you could ask, why is it relevant now? And in fact, one place where it does or can at least play a major role is simulating quantum circuits on a classical supercomputer. Okay, and this is something that people are doing now and they're quite interested in doing, particularly since the supremacy results came out, and people are thinking a lot about pushing the limits of classical simulation and maybe even solving hard quantum mechanical problems by encoding them in circuits and classically simulating those. Okay, so classical simulation is hard, we think. Otherwise, we wouldn't bother with building quantum computers. So all the known algorithms for doing classical simulation are exponentially hard in some measure of how large or how complicated the circuit is. So for instance, the number of qubits for naive simulation, memory goes exponential with the number of qubits. If I just want to do what's called state vector simulation. If I want to simulate with tensor networks, then the tree width of the circuit is actually more important, which somehow measures how entangled things are getting. But quite an interesting one is these kinds of stabilizer decomposition techniques where the relevant measure of complexity is actually the T count, or at least the number of non-Clifford gates, which the T gate is the kind of main example. Okay, so the way these things work is stabilizer rank decompositions simulate a hard circuit by summing over lots of easy circuits. Okay, so a hard circuit is a kind of a generic quantum circuit. And what I mean by lots of easy circuits is circuits in this Clifford fragment. Right, so these circuits in this Clifford fragment are efficient to simulate. Okay, so let me say what the stabilizer rank is. So the stabilizer rank of a state is the smallest n such that I can make that state as a linear combination of n stabilizer states. Okay, so these are these things that are efficient to classically simulate thanks to this Gottesman-Knil theorem that I mentioned before. So the amplitudes of stabilizer states can be computed in some constant times polynomial time. Or let's say can be computed in polynomial time, and then if I have n terms, then it's n times polynomial time to simulate such a state. Okay, so that means that if I can find good decompositions, I can do fast classical simulation. Okay, so if n is like 5, then I've won. I can simulate that thing just fine. Okay, so this, even this number, this stabilizer rank number, this capital N, is hard to compute in general, but certain upper bounds exist. So there are ways that I can do these decompositions. And one way to do it naively is that every time I encounter a T-gate, I can actually just break my whole circuit into two different terms. Okay, and I say that this is naive because to get rid of one T-gate, I end up with two terms, and then to get rid of two T-gates, I have to split each of those terms, so I get 4 and so on. So I get 2 to the T terms, where little t here is my number of T-gates. So people have come up with better ways of doing this. So there's this Bragi-Smith-Smolin decomposition, which is this kind of wild-looking thing here, which takes 6 T-gates and decomposes it as 7 stabilizer terms. Okay, so if I did that naively, I'd have to get 2 to the 6. I guess that's 32 terms. Here they found a way to do it with only 7. And if you work out how this scales, you see that rather than getting 2 to the T terms, I get 2 to the 0.4 times T terms. Okay, so these things still go exponential, but the name of the game becomes trying to get this fraction to be as small as possible. Okay, and that's kind of how these techniques work. Okay, so here's kind of a fun idea that we came up with when we were looking at this kind of wild-looking decomposition here. Was we would write it just as this wild-looking decomposition of ZX diagrams. Okay, so here's what it looks like if we decompose, say, 6 of these T gates or T spiders into 7 terms. So we can do this whole thing in the ZX calculus, but of course the question is, why would we do this? Is it just fun? Is it prettier? Is it just somehow more satisfying? And the reason why we might want to do this is the following. So if you think about, say I start with a circuit which has, in this case, 33 T-gates in it. Okay, and I want to start decomposing this thing as a sum of lots and lots of circuits with fewer T-gates in it. Well, so I'll take one round of decomposition, and now I will get, say, 7 terms, each of which has 27 T-gates in it. Okay, so there I've taken a single step of this decomposition. And then I'll take another step and I'll get, 7 times 7 terms, each with 21 T-gates, and so on. And this will produce this number that I was telling you about. So 7 to the n over 6, which is about 2 to the 0.4 n terms. Okay, and you could do this just with normal circuits and you wouldn't need all this ZX fanciness. But the cool thing is when you do this with ZX diagrams is you can start to interleave this decomposition with this simplification stuff that I was talking about before. So this optimization stuff. So you can start interleaving this decomposition with our simplifier routine. So what you do is you split up this thing into some terms, and then you optimize as much as possible, and then you split some more, and you optimize as much as possible, and so on. And what this can do is actually make the number of terms that you have to evaluate in practice significantly smaller than this 7 to the n over 6. And in fact, so for instance, see in one of these legs, maybe I'll get 0 T-gates left, and then I can just efficiently simulate the circuit that's at this node. Right? So that's cut off a whole kind of subtree of this procedure. So how well does this work? Well, we tried it on a couple of families of circuits. We tried it first on random circuits, which we were constructing in a certain way. And we started looking at, with these kinds of heuristics, it's hard to know exactly how long it's going to take. So a kind of thing we did was we said, okay, we'll just let this thing run and then we'll cancel it after 5 minutes and we'll see which of them succeeded. Okay, and as you can see, if the thing had 10 T-gates with 50 qubits or 100 qubits, they all succeed after 5 minutes, and they all succeed with 20 T-gates, and they all succeed with 30 T-gates. and then things start to dip off. But one thing to notice actually is that the 100 qubit circuits are actually more successful at simulating up to higher numbers of T-gates. In fact, because they're more sparse. Okay, so this circuit being actually a bit sparser makes this technique work better, even for more qubits and the same number of T-gates. Okay, and if you look at how much this saves us in terms of actual work we're doing, then if you compare the number of terms that we had to sum up in the end to this naive decomposition, we're saving, by the end, we're saving something like 15 orders of magnitude. So this can make a big difference versus this naive approach. But with the random circuits, actually what already does a lot of this work for you is the initial bit of simplification. So if I do just a single round of T-gate reduction, then I compare that to this kind of interleaving procedure, then you can see that, well, at best, I can improve things by kind of a factor of 30, which is still quite good, but it's maybe not quite as dramatic as you might expect. But then if you pass to structured circuits, so there's this other family of circuits that people have considered for classical simulation, which solve what's called a hidden shift problem. Then these results, I think, were quite dramatic. Okay, so the sizes of circuits that we were able to simulate here was well, I was completely surprised by this. So here again, you notice now this graph is starting at 70 T-gates rather than finishing at 70 T-gates. And at 70, we were 100% successful. But even at well over 1,000 T-gates, so now you're talking, far beyond the age of the universe to simulate such a circuit with the naive strategy, still we're succeeding about 15 to 18% of the time. So this was quite dramatic. And if you see what kind of reduction factor we have in the numbers of terms, then right here at the edge, we are reducing things by almost 400 orders of magnitude. Okay, and even comparing this to a single round of simulation, this kind of interleaving ZX and decomposition trick is improving things by like 8 orders of magnitude at the top here. So what this shows, I think, is that this can already buy you a little bit for random circuits, but even if there's some structure that our rewriting can start to exploit, then this really buys you a lot. Okay, so that's basically the two things that I wanted to talk about. Well, 3 things really: this optimization, verification, and classical simulation. So the question is kind of where this whole program is going or what to do next. Well, one thing is to look at new kinds of optimization, and this is kind of a balancing act, because the more aggressively you optimize these diagrams, the harder it becomes to get circuits back out of them. Okay, so in fact, we're thinking about ways where you can optimize by using some sort of scratch qubits, but there's some sort of hard problems around doing circuit extraction there. Doing more general and effective routing for circuits. We're thinking about doing better classical simulation and also mixing with some of the tensor network-based techniques that people are using in condensed matter and also in quantum circuit classical simulation. Trying to do things that go in a direction of something like static analysis for quantum software. So we can already kind of under approximate equality in that we can prove things that are equal or we don't know. The question is, are there ways that we can kind of over approximate it? So can we find things which will say these two things are not equal or we don't know? And we can start to try to bring in things like functorial semantics, so basically giving different kinds of interpretations for circuits or for diagrams to try to prove things are not equal efficiently. And I think this would be a quite interesting thing to try. And also to try to use ZX and try to use the pictures as a kind of a glue for a big compilation architecture. So you can think of ZX calculus as this kind of intermediate representation where lots of programming languages might compile to ZX, or here I think we call this augmented ZX or annotated ZX. And you can imagine using this thing as an intermediate language, which then compiles farther down to different kinds of computing models and ultimately down to different kinds of hardware platforms. Okay, and getting all of those pieces to work together in a useful and interesting way, I think, is a big project that will keep us and maybe a lot of other people busy for a while. So that's it. Here's some references, and there's probably somewhere I can make these slides available afterwards. And so here's the kind of the framework paper where we talk about reducing and extracting circuits. Here's the routing paper, which incidentally was independently discovered by this group, a very similar technique. So I put the ref there for that too. And the most recent stuff is this classical simulation thing, and you can find it in this paper here. And also the kind of these two are the kind of most active open source projects kind of around this. So with that, I think that's all. And I see there's a couple of questions already, and I'm also happy to take any others.
Yeah, Aleks, thank you so much for a fascinating talk where I think all of us learned a lot of very useful approaches to make quantum computing a little bit more easier and more straightforward and accessible. Ilya, would you like to guide us through the question, please? And please,
yes, we have two questions.
Remind the participants that if they want to speak the question in person, they just have to raise their hand and we can give them the right to speak. Yeah. Ilya, sorry.
Yes, I just given the right to ask his questions to the Daniel. Daniel, go on.
Hi, thanks a lot for the very nice talk. My first question was whether this prefactor in the exponent actually exists, right? Where I mean, you can decompose an n-qubit magic state as a linear combination of the stabilizer ring, right? Mm-hmm. Is it proven that it scales exponentially and people are looking to lower and upper bound this exponent? Are there no lower bounds now known for this? If this makes sense.
Let's see. So yeah, and indeed there's upper bounds that are known. I mean, essentially every time you give some kind of decomposition strategy, this gives you a new upper bound, and this keeps getting pushed kind of lower and lower, kind of every 6 months or something. As far as I know, there is no lower bound that exists. Now, if indeed this were Pauli, then this would imply that BQP is efficient. So that BQP is in P. So this is very unlikely to have a polynomial, a generic polynomial realization. But then, you know, for some given state, it could be the case that it has a very low stabilizer rank. And in fact, this is the kind of, I think the lesson of using these kinds of ZX type techniques is that when you're looking at a very specific state, these things can have quite low stabilizer ranks. You just need some good heuristics to find them.
Do you think it is hard to derive a lower bound?
I think so. I mean, you also need to think a bit about how you would want to state this. I mean, I guess you could try to derive a lower bound for something like a Haar random quantum state or something like that, and try to use some fact about that it won't.
No. I think the interesting state is the n-qubit magic state, right?
Oh, okay. So you mean specifically for the n-qubit T gate?
Yeah.
or T
Yeah.
magic state.
Yes.
I think still that's not known. I think there's no
Okay.
or there may be a lower bound, but it might be very low, actually. So as far as I know, there's no exponential lower bound that's been derived for this one.
Okay, thanks. And my second question is whether or not these techniques have been applied to simplify variational ansatz circuits for VQE, for example, right? Because there you might have chemically inspired ansatz, right? And that is like a long circuit, maybe trotterization, I don't know.
Mm-hmm.
And then they want to squeeze the circuit down to reduce the depth, right? Has this been done? Are you aware of this?
So there's been some kind of smallish student projects around this. I think the results kind of somewhat inconclusive at this point. One of the things we are quite interested in doing actually with the tools at the moment is extending them to work with symbolic angles for various reasons. So right now, for instance, this PyZX tool, it stores the phase angles as just rational multiples of pi. But there's no reason that couldn't also hold some sort of, either just a variable or maybe a polynomial in several variables. And you could try some heuristics for doing kind of parameter space reduction and this sort of thing.
Interesting point.
It's not clear how well that's going to work yet, because those kinds of parameterized things are sort of opaque. So there aren't a lot of things you can do with them, but you can start to sort of commute things around and combine them in various ways. So I think there is some scope for doing that.
Thanks a lot. That was really very insightful.
Okay, thank you. Jeff, you can ask your question. Okay, I'm not sure why the Jeff. Maybe Jeff, can you unmute yourself? Okay, maybe
Yeah, did you
Zurab
mean
can
Jeff
ask
or
his
did you mean
question
myself?
first. No, I mean Jeff, because his question is in Q&A. But okay, Zurab, go on, and maybe Jeff will react. Okay.
I can also answer just the text, but maybe he would like to ask it his voice.
Okay, maybe let's do the text version of the question. Okay, the graphical circuits optimizes poorly written code. Such code is frequently incorrect. The approach taken by the PRG was instead to support the top-down development from spec to code. Response?
Okay, I mean, I now see that this is intended to be a provocative question, I guess, because he says to respond. I wouldn't say that circuit optimizers optimize poorly written code. I mean, yes, in some sense they do, but they also will optimize code which arose from a generic procedure. Okay, so for instance, if I want to write some sort of complicated function which works for any number of qubits, typically I'll write a recursive function that does this, and this is totally generic. So I can give it a parameter and then it will generate me a concrete circuit. And now the place that I want to apply optimization is after this concrete circuit has been generated. So you can imagine, if I've got a loop or some recursion, the things at the beginning of the loop will start to cancel with things at the end of the loop. And the fact that you can get some traction with an optimizer like that is not necessarily because my code is poorly written, though if I write inefficient code, maybe I'll find more optimizations. But because the code was not fully concretized yet. So if you're doing optimization right before it goes to the hardware, the code is somehow fully concrete, and you should be able to find more optimizations than you had before. Now, that being said, I think you always want to combine this with both with code generation and a kind of a code style, which is in some sense efficient. So I don't see these things as kind of competitors to each other for making efficient code. I see these kind of, you know, good development discipline along with good compilers and optimizers are all kind of important things to create efficient code. I don't know what this PRG thing is, but maybe you could put a link or something in the chat so I could have a look at that.
Okay, let's see if the Jeff responds, and meanwhile, Zurab, you can go on.
Thanks, Ilya. Could you please go back to that slide where you showed us the 8 rules?
So this was the one quite near the beginning with the universal set of rules.
Forgive me if you already answered this in your talk and I didn't catch it, but I was wondering whether, I mean, so when you try to use these rules to reduce the diagrams, whether it's possible to set it up in such a way that you always shrink the size of the diagram with the application of the next rule. I know that you discussed it for some of these, but then the others were left out. And does one have to sometimes increase the size of the diagram, or do they always shrink? Yeah.
So this is where it becomes important whether you're focused on a tractable fragment of the language or not. So the fully universal language is where these parameters are allowed to be any angles. Okay, so these are actually just a real number of parameters that can be any angle, and that's universal for quantum computing. So you wouldn't expect to have a rewriting strategy which both is always reducing the size of your circuit or your diagram, and also gives you uniqueness in some sense, like unique normal forms, or at least normal forms that can compare to each other efficiently. Because that would imply that I have an efficient classical routine for basically for simulating or for comparing circuits. There is a way that you can use these rules to get normal forms, but they, as you say, they grow. So you can get normal forms which are unique, but they grow exponentially large. And that's because you're in this universal intractable family. So that's kind of one thing you can do with the calculus. The other thing you can do is you can focus on a tractable fragment like the Clifford circuits. And there indeed you can find a way to apply the rules which always reduces the size of your diagram. And eventually you get to a normal form which is only quadratically large in the number of your qubits. But this really has to do with the fact that you're then focusing on some family that's efficient to work with anyway.
So if I want to, back in the original context, if I want to show that two things are the same, would it be possible to do it by trying to kind of jointly reduce them, or would I have to expand them first?
So you're a fully generic procedure. So an algorithm for doing this will almost necessarily need some kind of expansion. The thing will need to grow. In practice, you can often do better than that. So if there's some specific pair of diagrams that you're trying to relate to each other, you might not need to blow things up to exponentially large. You might have an efficient proof strategy for this.
Thank you so much.
Okay. And I think Jeff responded, or somebody responded in the Q&A, that PRG stands for Programming Research Group.
Oh, okay. Oh, so it's not specific to a programming research. Ah, right. Yes.
Okay.
Yeah.
Otherwise, yes. There is no more questions. Francesco, yes, you can take over.
No, thank you very much, Ilya. Then before I thank Aleks, I would like to again extend the traditional invitation to everyone to join us in Kumo Space for a little virtual social interaction with the speaker, who indicated that he is able to join us as well for a short while. I put the link in the chat. So if you open the chat, you will see the link to Kumo Space. You just copy and paste it in your browser. Don't use Safari, it works better in Chrome and in Firefox if you have it at hand. Aleks, then thank you so much for this very interesting talk. We had a very attentive audience today who was really interested in hearing about these new tricks to simplify quantum computing algorithms. So thank you very much for your time, and I'm looking forward to chat to you in Kumo Space just in a few clicks, in a few seconds. Yeah. So thank you very much, everyone. We will be again here next Monday for another interesting colloquium, and tomorrow our mini school on Haskell continues at 2 p.m. So if you attend everything, we will see you again tomorrow afternoon. Alexander, thank you very much, or Aleks, thank you very much for your time. It was a real pleasure to have you here, and hopefully there will be lots of people in South Africa starting to use the software that you developed. So thank you very much for introducing us to that. Thank you. So each of you have a good afternoon, and still be careful because COVID is still out there waiting for us. Yeah. So thank you very much. Have a good evening, and I will chat to you in Kumo Space, where as usual all drinks are for free. Yeah. So thank you very much. Bye.